Okay, hello everybody. So this is this problem we have A and B. So A is using the notations of maps, parameterize the circle of radius r. So some fixed positive number radius r denoted, and so here's just a symbol for like r times the unit circle. So the unit circle is S1, and r times it is a circle of radius r. And it lives in the plane. And so parameterize it using square roots, trig, and rational functions. So there's sort of three parts to part A. And part B is the same problem, but now for the sphere. The unit sphere is a two-dimensional surface of a sphere living inside of three-dimensional space. Okay, so part A, square roots. So we'll do square roots, and then we'll do trig functions, and then we'll do rational functions. Okay, so square roots. So sort of the equation for a circle of radius r is that the sum of squares be r squared. And so I can either choose solve for x1 or x2. And let's say I solve for x1. And then at this point, I could again have a choice of two things. I could do the positive square root or the negative square root. So we'll just pick one of them. Say the positive square root. So now I've sort of, okay, so what does it mean to parametrize the circle? It means I have to give a map that gives the circle, or at least part of the circle, as its image. And so if my coordinates on R2 are x1, x2, as I've sort of already chosen there, I could say coordinates are t here. And then I want to produce a map. So I'm going to send t to the point. So here I've shown how to replace x1 with something involving x2. So then what that means is I can replace x1 here with something involving only the parameter x2. And so I'll take the positive square root, and then I'll put a t there. So now what I've done is I've just renamed the second axis x2. I just renamed it t. That's what this second component function is doing. And then I replaced the first one by this value. And so what this will give me is sort of my parameter t is secretly the second component axis, like that axis right there. And since I chose the positive square root, this will give me the right half of the circle. It's missing this left half. Okay. Or I could use the map t goes to minus square root of r squared minus t squared, comma t. And that would give me the left half of this circle. Let's say this is the point, 0, comma r, because this is a radius r circle. And now I'm missing the right half. That's this map here. I also could instead have, instead of solving for x1, I could have solved for x2 and then done the entire thing, and then chosen the horizontal axis as my parameter t, and then chosen the positive square root, and this would give the upper half. Or, keep writing or everywhere, or I could have chosen this sort of looks like a t. That's actually just a plus sign. This is the problem with t's. T's and plus signs look the same, which is why I always try to make my t's with a little curl at the bottom. Now I have the minus square root. And that gives the bottom half of the unit circle. Obviously, these are all just different drawings of the same unit circle. Okay, so that's how we do it with square roots. And note here that in all these cases, I wrote the map from R to R2, but actually this map isn't defined on all of R. It's only defined, well, okay, so this part of the function has no problem. All those parts are defined on all of R. But if I try to plug in some inputs where t is bigger than r, or smaller than minus r, then this will be a negative number inside of there, and the square root won't know what to do with it. So sort of actually this map is defined only on the interval. This is notation. This notation here means on the real line, we just, if here's 0 and here's minus r and here's plus r, this notation means the interval between and including the endpoints minus r and r. Okay, that's square roots. Now we need trig. So again, we need a map parametrizing the circle of radius r. And on that circle, if that's r, then what we have here is a triangle. I'm going to sort of zoom out and I'm going to redraw this triangle larger. This distance, this hypotenuse, is length r. And so that's a right angle. And if I call this angle theta, then what you should just immediately memorize is that these legs, this opposite leg, the leg of the triangle that is opposite theta, is r sine theta. That's a theta, not a 0. And this leg that's adjacent to the angle theta is r cos theta in length. And so this you should just memorize it. Make this picture your friend. It's going to come up everywhere. And from that, I achieve my parametrization. Let's take t to r cos t, r sine t. We could also have called this number line by call an arbitrary element theta, and then we could just use r cos theta, r sine theta. Okay, and note, so I'll put this in quotes, polar coordinates doesn't just parameterize the unit circle by this map, but actually parametrizes the entire plane by the map now where I let r be a variable in each of these component functions. This is just sort of me saying, I'm going to now let r vary. And so now I have a map from R2 to R2, sending r comma theta to exactly the same map. And this map will be very important for us later. Okay. And the last one is rational functions. Rational functions. Here I'm abbreviating the word functions with F, C, and S because I find that abbreviation useful as I'm thinking and writing out my thinking. Of course, you would type this in any sort of mathematical paper or presentation. Okay, so now rational functions. So as for now, I just want you to be familiar with this. And so essentially, for now you can even memorize it. Later we will see it geometrically coming from something that you should look up, at least on Wikipedia, from the stereographic projection. And this is just roughly like if we have here the unit circle living in the plane R2, and if we take a point from, let's say, the South Pole, and we go to some point on the horizontal axis, like there, and we draw a line, straight line, then that straight line is going to hit the unit circle somewhere. If I go to this point, then the line will hit the unit circle there. If I go to the point 0 on the horizontal axis, then it'll hit the point on the unit circle sort of that we'd call the North Pole. If I chose this point, it would hit this point, etc. And as I go and choose points farther and farther away, my straight line will hit the unit circle closer and closer to this South Pole. South Pole. Okay, so what this turns into is a parametrization of the circle using the horizontal line as an axis, or as a parameter, and it's sending t to the number 2t over 1 plus t squared, comma, 1 minus t squared over 1 plus t squared. And these are ratios of two polynomials. The top and the bottom is a polynomial in each of the component functions, and we call that a rational function. Okay, so for example, 0 goes to the point 2 times 0 divided by 1, 1 minus 0 divided by 1 plus 0 is 1. And so here we get the North Pole. The point 1 goes to, well, it's this picture. If I chose the point 1 on the horizontal axis, I draw the line, and actually it hits the unit circle at the point 1 itself, or at the point 1 comma 0, and this is what we should get. If I plug in a 1 there, I get 2 over 1 plus 1 is 2, and 2 over 2 is 1. Here I will get 0. If I take 1/2, I get 1 over 1 plus 1/4, comma, 1 minus 1/4 is what, 3/4 over 1 plus 1/4. So if you want, you can simplify this. This is like 5/4. So this is 4/5, comma, 5/4 down there, and I'll get 3/5. And sure enough, this squared plus this squared is equal to 1. Okay, but didn't we want the unit circle of radius r? So then actually our map should be send t to the point r times 2t over 1 plus t squared and 1 minus t squared over 1 plus t squared. And I wrote the r out here, but the way we multiply a vector by a real number is that it comes into each of the components. And so I could have written 2tr. I don't know why I put it over here. I could have written r times 2t and put it right there. But either way. And then I also need to put the r over here. So maybe I'll write like this. But of course, this is the map that I think you should memorize. And why, we'll talk about this later, but this map is useful for exact computation. And that can be very helpful in many circumstances, because here we need to calculate a cosine and a sine, both of which in general we will have to approximate. And over here we'll have to calculate a square root. And again, we cannot calculate this exactly. We know the square root of 4 exactly. That's definitely 2. But what's the square root of 5? We can't. We have to approximate it. And so if we would prefer to have exact calculations, then we can use this rational parametrization of a circle. Okay, so there's the square roots, the trig, and the rational functions. You just need to know the maps. So this map and this map, this map, and really just one of these maps. And you're only parametrizing a part of the circle, but that's sort of the point. Okay. Let's do part B. Parametrize the sphere of radius rho with square roots, trig, and rational functions. Okay, so let's do that over here. B. Sphere in square roots. Okay, so now the sphere, of radius, I called it rho because later in physics, they will often call, instead of r, they take rho in three-dimensional space. And I don't know why, but, rho is /rho if you're typing in LaTeX. Or, it's just this sort of curly p. It is a Greek letter. And I like to make it a little curly to distinguish it from the letter p. Okay, equals rho squared. And so I can just choose one of the coordinates and solve for it if I use a square root, and I'll have to choose plus or minus. And so we're only going to get half the sphere. But then that lets me replace, let's say I solve for the third variable, then I can replace the third variable with something involving the first two. So for example, I can take x1, x2, and map it to the point x1, x2, and the square root of rho squared minus x1 squared minus x2 squared. And you see that, I could have called this t and s, or say t1, t2, and mapped it to t1, comma t2, comma the square root of rho squared minus t1 squared minus t2 squared. But all that would have been doing is just sort of renaming these first two dimensions as t, and they're just equivalent. It's just a, what's your choice of naming variables. And I like to point that out because that confused me a lot as a student. This is just choice. It's your choice is how you name variables. So yeah, let's just keep them in this case as x1, x2. Well, then this is a map from R2 to R3 because I have 1, 2, 3 component functions. But there's another map, which is I could have taken x1, x2 to the point x1, comma x2, comma minus the square root of rho squared minus x1 squared minus x2 squared. I also could have chosen, say, x1 and x3, and then solved for x2, move the other things over, take the square root, which could be positive rho squared minus x1 squared minus x3 squared, comma x3. Or I could have chosen the negative square root, and this would give me sort of the left or right pieces of the sphere. And so now I could also have chosen x2, x3, and I could have solved for x1 up here in terms of x2, x3, and that would give me another map, say square root of rho squared minus x2 squared minus x3 squared, comma x2, x3. So now the x2 and x3 are the same as my parameters. Or I could have taken the minus. So these are actually 6 different maps. Now let's just see what they are. Like if I draw, this is the x1 axis, and let's say this is the x2 axis, and this is the x3 axis. Let's see, what is this map doing? And compare it to what is this map doing. So what we're doing is we're using the x1, x2 plane as parameters in those maps, and then we're getting the top or bottom halves of the sphere. So like maybe this is the top half of the sphere, and we're missing the bottom half. So I'm not doing a great job drawing this, but this is the top half of the sphere. Whereas this map down here would give the image of this map would be the bottom half of the sphere only, and it's sort of missing this top piece. Over here, these maps are the right and left. You can see this is happening in the x2 direction. So if I keep my same x1, x2, x3 like that, then I either have the right, okay, this is harder to draw. This is supposed to be the right half, compared to the left half over here. Wow, those are terrible drawings, but you see the point, and then here we have the sort of front and back halves. Yeah. Okay, great. So that's the square roots. These maps only give half of the sphere. We need trig now. The trig sphere. Okay. So this is really important. So I'm going to try to draw this well. And we're doing this now because it's going to come up in your physics classes, in your chemistry classes. It's going to come up in future math classes. It's going to come up in this math class in like many, many, many future problems. And so let's just learn it so we have some time for it to sink in. And let's learn it right now. So this is just an arbitrary point. Let's say this is point x1, x2, x3. And I've drawn it. This is really the only point I draw in 3D. But it's supposed to be an arbitrary point. Any point in 3D will have a similar picture. So this is my cartoon. And now what I have is that this point is on the unit, or not the unit sphere, the sphere of radius rho. The sphere of radius rho. And so this length here is rho. Okay? And then what I want to notice is that if I draw on this piece, I get a triangle. Well, let me see. So above this piece here, there's a piece above it, like that. And what I want to do is I want to use this angle. I think it's maybe psi, like PSI in LaTeX. The psi is a Greek letter. I'm not really exactly sure what it is, and then I want to use this angle, theta, and those are my two parameters. So this is longitude and latitude on the Earth, and these are, the coordinates of a spot on the Earth in longitude and latitude are basically these two angles. And so we're going to use them to parametrize the sphere. We're going to take a map from, the sphere is two-dimensional, so we need two parameters for a two-dimensional sphere. And the sphere lives in 3 dimensions. So this means we need to take theta and psi to something, something, something. And, what are these 3 component functions? That's what we need to discover. To discover them, we look at this drawing. So let's first look at this triangle. So I'm going to redraw, see this triangle here. I'm going to redraw it. And it's one of our familiar triangles. So here is my psi, here's rho. And then immediately, this is one of those things you memorize, as I said before. The opposite of this angle is rho sine psi. I want to say phi. There's phi and there's psi, and I can never seem to tell the difference. And then this one is the, adjacent to this angle. This leg has length rho cos phi. And so that means we immediately know the z-coordinate. And so this, this one right here, this is obviously this is the z-coordinate. Well, it's not obvious. It's not obvious at all. But when you look at it for a moment, you realize that that distance is the z-coordinate of this point, or the x3 coordinate. It's the coordinate in this vertical dimension in my drawing, and that should be rho cos squiggly phi psi, whatever it is. Okay, so that was from this triangle. But now I realize that, this top piece here is there, which is the same as there. And now we have a triangle that has theta, so now we can get theta involved. As long as I remember that this is rho sine phi. Okay, so now I got my second triangle. which I'm going to redraw. And this is now my theta, this is 90 degrees. And so then this is rho sine phi. Okay. And now, instead of r, so this is opposite. Here we have the angle, and now over here is opposite, so that gets the sine. That is the sine of theta. And here's angle theta, and this is adjacent, so that is the cos of theta. But then we have to multiply by the length of the hypotenuse, which in this case involves two things, the rho and the sine of a completely different angle. And this gives us our second and third component functions. Here we have the rho sine cos, and here we have the rho sine sine. And so that is our map. Okay. So, here it is. I think it's clear which is the first, second, and third, although you wouldn't see this written that way in a paper, for example, with these little squiggly lines coming out. But for this, it's good enough. And now, again, I will note that, note spherical coordinates, which are quite confusing as a student. They come right out of this. Now, instead of finding just the sphere of radius rho, we let rho vary. We let rho vary as a third parameter, and that just expands the spheres out in radius, and all those spheres from very small, almost zero radius, all the way out to infinite radius, fill out all of three-dimensional space and give us spherical coordinates on three-dimensional space. This is very important because when a problem has spherical symmetry, you cannot solve it. You cannot solve it until you utilize that symmetry by changing coordinates. And so this will be the changing coordinates map. It is rho, and now, what was it? Sine cos, sine phi. Oop, not comma. This is all multiplying. Cos theta. Rho sine phi sine theta. And rho cos phi, I think it was. Let's double check. Yes. Okay. And now we're almost done. We just have rational functions. Let's go back to a different color. Rational parametrization of the sphere. And this is the stereographic projection that I mentioned before that you should look up on Wikipedia. And at this point, I think you should just be aware of it. It gives you a third way to look at a sphere. And here's what it does. So remember, our previous map was like this. This was the rational parametrization of a circle. And so let's take T1, T2, and let's map it to 2T1 over 1 plus T1 squared plus T2 squared, comma, 2T2 over 1 plus T1 squared plus T2 squared, comma, 1 minus T1 squared minus T2 squared over 1 plus T1 squared plus T2 squared. These are three rational functions. You can see they're pretty straightforward generalization of this. And later we will talk about the geometry that gives rise to them. But for now, this is our map. This is a rational parameterization of the sphere. It allows calculation of exact coordinates, exact rational number coordinates on the sphere. This is a map from R2 to R3. And let's see. We want it to be of radius, the sphere of radius rho. So I'll just multiply each of those components by rho. You could put it here, which actually I prefer. Or, it's identical to putting it like here. either way works, but I actually prefer it to be out there. Okay. So there we have it. We now have seen, basically this problem is to learn about maps. Like, what do they look like? What are some useful maps? Some involve square roots and, give you half and have difficulty when they're negative numbers. So actually it's not a map defined on all of R2, but only on some special pieces of R2. Then there's Trig, and Trig is great. It's probably the simplest. It gets every point on the sphere. It gets every point on the circle. But hidden in there is the complexity of how do I calculate sine? How do I calculate cos? And then lastly, we have irrational functions. And those are the easiest to calculate. They're exact calculation. But the formulas start to get a little bit difficult for humans to comprehend.